So you're like a science sponge.
Yeah, or a science gadfly. To some extent.
You're listening to The Cosmic Cast.
Hello everyone and welcome to the three-tiered wedding cake that is The Cosmic Cast. You're here with me, the delectable New York cheesecake, Rick Viver here. To my right is the French fancy, Tom Harvey. In front of me is the jam roly-poly with custard,
Lovely.
Dr. John Bernard Fisher.
Hello.
And today we have an amazing guest for you all. Adding the cherry on top of this cake is Professor Jamie Gilmour.
Hello.
Hello, Jamie. How are you doing?
I'm doing very well, thank you, Ricky.
And Tom, how are you?
I'm doing pretty good.
And John?
Oh, I'm pretty good, thanks.
Grand, let's crack on.
Although just a small note, I don't actually like custard, so if I get the custard removed from the roly-poly, that'd be quite good.
Okay. I'm not going to do the whole intro again.
So Jamie, you are a planetary scientist, and you're particularly known for doing high-precision xenon isotopes. But I think the first question I really want to ask is, did you choose xenon, or did xenon choose you?
Oh, Xenon chose me, really, because I always blundered into this career. I finished my undergraduate degree in Sheffield, and I was thinking about what I would do next, and I happened to bump into the head of school at the time, who was Professor Grenville Turner, who was a fellow of the Royal Society, and he was saying, well, you could stay on here and do a PhD. And so I was looking at the PhDs that were available, and there was one in solid-state physics. And I was going to do that, but then Granville said, well, I've also got this PhD in developing instrumentation for measuring things in meteorites. Would you like to join that group and do that? So I did that and started building a mass spectrometer, which was aimed to measure xenon isotopes in meteorites, I found out. So most of my PhD was just trying to get the thing to work. And even after that, I started as a research scientist, carrying on developing that instrument. It didn't really start working until, let's see, about 8 years after I started my PhD. It was working in a usable form. And then we started analysing samples, and I realised that if I was going to carry on with this, I was either going to be just somebody who ran samples through a machine for other people, or I had to get interested in the actual science behind it. And so that was how I got into xenon isotopes. I built a machine that happened to analyse xenon isotopes, and then got bitten by the xenon isotope bug.
As you do.
And the rest is history, I suppose. That's how I ended up doing what I do. I'm still working on that instrument, or it's what it developed into is downstairs in the lab right now.
Wow. So it's basically your child, that instrument is then.
Yeah, in a sense.
And so did you do this all at Manchester University then?
Well, the project started out in Sheffield, which is where I did my PhD, and then, so that was 1985 when I started my PhD, and then 1989 we moved to Manchester and moved the whole thing over the Pennines, put it into a lab downstairs, and carried on with the development process, at which point I was a postdoctoral research associate.
What was the reason for the move?
It was kind of, it's back in history. There was a time at the end of the 80s when people were looking at bringing science departments together, so that rather than have a geology department at every university, they would try and have a few centralised bigger geology departments. I think it was called the Oxborough Review. And so this was the plan, and so Manchester put together a bid to become one of these geology departments, which was successful. And as part of that bid, quite a few groups moved here to this department, and the department changed quite drastically. It grew at that point. And then that's kind of the history of how things started off. So it was part of that consolidation of earth sciences in various bigger departments. But that movement died out gradually, and so things went back to more universities having geology departments again.
And now you're the head of the Planetary Science Department at Manchester University.
Yeah, I lead the planetary science research theme.
And when did that develop? When did it go from just having geology to having also a planetary science?
It was all part of our research group. It was always, I suppose, a planetary science research group. We used to call it, or we call it cosmochemistry. It's broadened out its interests a long way since then, and so it's become a theme that a lot more people are interested in now than just the isotope geochemistry people, which is where the group really started. So my PhD supervisor had been one of the first people to date moon rocks when they came back with the Apollo 11 program. So that's the history of it, and developing argon-argon dating, which found applications across earth sciences. And so that was our sort of the starting point of planetary science. And then since then, partly through teaching and partly through broader research, people have developed lots of different new interests. There's a lot more people working in the area now, and so we have a more diverse and a wider theme.
You've always been situated in the UK. Have you ever felt like you'd want to go to a different country to research, or?
I actually spent a year in Tennessee
Okay.
in the end of 1999 through 2000. I did a sabbatical at the University of Tennessee, where I was working on a similar sort of instrument to one we have downstairs, but this was aimed at analysing krypton isotopes. So that kind of gave me a lot of different experiences, and now we're having a broadening out of that instrumentation to do xenon and krypton together. It was just built on my experience in Tennessee. Right. So the thing that makes it harder to move around is, my research is very much focused on this unique instrument, and so we're the only place that has an instrument like that. And so it'd be quite a shift to go to a different organisation and maybe start building from scratch again.
So do you get a lot of people coming from other establishments over here then to use the instrument? We
have a fair number of visitors coming, bringing samples if they want. What our instrument does is it analyses smaller amounts of xenon than any other instrument can do. And so if people have limited amounts of samples, say a single grain of some material, and they want to analyse it grain by grain, then we're the logical place to come and do it. And so we have people come and do that sort of analysis here.
What is it about xenon that makes measuring it in such small quantities important?
Well, there's loads of things about xenon that make measuring it in very small quantities really important. It basically comes down to the fact that xenon has 9 different forms. So there's nine isotopes of xenon. So chemically they all react the same way, which is to say they basically don't react with anything at all in the natural environment. So if you think about a planet like the Earth, xenon's acquired by the material it's built from, or it's trapped from the gas as the Earth is growing in the early solar system. And as it gets processed through geology, if ever it ends up in the atmosphere, it's more or less going to just stay in the atmosphere. So what we're breathing in and out at the moment is xenon that's been outgassed from the centre of the Earth over about 4.5 billion years of its history. So the chemistry is always the same, but these 9 isotopes have different nuclear properties. So some of them are produced by radioactive decay. So plutonium produces a set of xenon isotopes when it undergoes fission. Uranium fission produces a set of xenon isotopes. There's an isotope of iodine, which was very short-lived. It only lives a few million years, but it was around in the early solar system, and that produces one of the isotopes of xenon. And then you can think about where they came from. So all of the matter, apart from hydrogen and helium, pretty much was made in stars before our solar system formed. So, but they don't all make They don't make things as xenon, they make particular nuclei. So one sort of star will make one set of xenon isotopes, another sort of star will make a different set of xenon isotopes. And if you look at primitive material like meteorites, you'll find little grains that actually condensed around individual stars before the solar system formed, things we call pre-solar grains. And they'll have the signature of the xenon that was being made in that star just before it came to the end of its life. So you can disentangle all the sources of material that contributed to the solar system and try and trace that pathway from making elements in stars right through to planetary atmospheres and see how these things mix together and use the radioactive decay to look at timescales and when things happened early on in the solar system. Because xenon has these 9 isotopes, you've got a lot of opportunities to disentangle the various things that contributed. Whereas other elements with fewer isotopes, if you have 8 different processes and you only have 3 isotopes to go at it to try and understand it with, then you can't disentangle that problem. But if you've got 9 isotopes, you've got some hope of seeing 8 different processes. So all of those things put together, and the fact that mostly we look at material that's trapped in solid grains, and because xenon is so volatile, not much of it is trapped from the everyday environment. So anything weird, any sort of radioactive decay product or any sort of nucleosynthetic product will stand out like a sore thumb against that background. So it's easy to spot anomalies in small amounts of material. So it's a useful thing to be able to do, to analyse very small amounts of material, which is what we do.
But they're quite challenging measurements to make, I guess. Would that be a fair thing to say?
Yes. It's a very specialised technique to get down to the point where you can detect, around about 1,000 atoms of one xenon isotope against the natural background of what's present in the Earth's environment. So yes, we have to use quite a specialised approach to measure those things.
Yeah. So it's quite cool. So you use lasers, don't you, to try and...
We do, yes. So the thing about lasers is you can tune it to just one frequency, essentially, and atoms absorb light of some frequencies and not others. So we pick out the frequency that xenon will absorb, which excites the xenon atom, and then once the atom's excited, you can ionize it much more easily, and so you can ionize it from that excited state with another photon from the same laser. So that's a process called resonance ionization, and it's really efficient provided you get the gas inside the volume that's illuminated by a laser beam, which once it's focused down is less than maybe 0.5 millimeter. So you've got to concentrate the xenon you want to analyze inside that, and once you've got it out of a sample, it's more or less floating free within a mass spectrometer, which might be as much as a litre in volume. Mm-hmm. So what we do is we create a very small cold spot in our mass spectrometer, and the xenon's continuously condensing onto that. Every time an atom hits that cold spot, it'll stay there over the lifetime of an experiment. So we're building it up on that cold spot and continuously heating that with another pulsed laser. So each time a laser pulse hits it, it releases the gas that's trapped on that cold spot, and you get a little plume, and then we fire the ionizing laser through that plume, so that when that very efficient ionization process happens, the sample gas is concentrated inside the volume that's going to be ionized. And that's what makes it the most sensitive instrument for xenon analysis in the world.
It's very cool, really, to think you've got ions of xenon flinging around that's come from a primitive meteorite that formed from the beginning of the solar system. It's quite a big picture sort of get your head around, isn't it, when you actually stood there in a lab looking at numbers on a screen pumping out.
Yeah, I mean, it's a bit like the fool on the hill, isn't it? You see the sun going down, and the eyes in your head see the world spinning round, or you see this strange trace of a xenon isotope ratio on a mass spectrometer readout, and you infer the presence of a supernova 4.5 billion years or more before the start of the solar system. So, yeah.
You recently had a paper out, and what was that focusing on then? So obviously you're looking at xenon isotopes.
Yeah, well, that was a bit unusual for me, because it wasn't actually based around analyses we did in Manchester. Okay. It was using some literature data that had been published quite a long time ago, and just trying to maybe look at it in a different way. So if you take apart a primitive meteorite, it looks like a lot of grains that have all been sandwiched together somehow. So we have this backdrop idea of the formation of the solar system, where you start with a cloud of gas and dust which collapses to form a disk, and the disk is going to feed material into the center where the sun is forming, and the planets form in that disk around the star. And that's a first order understanding of how the solar system forms. So if you look at that disk, it's kind of cooling down, and grains are forming, and the grains are sticking together, and then
they're sticking together because of gravity pulling them together?
Well, not really, because they're far too small to be affected by gravity at that point. So it's kind of an uncertain question as to what it is that allows them to stick together. Okay. Maybe it's because they have moisture around the outside of them or something. But somehow or other, they begin to accumulate to form bigger things. And so you get to a stage where there are what we call planetesimals, which would be around about 50 to 100 kilometer diameter things, a bit like asteroids today. So you can focus on that stage of solar system formation. Most of those planetesimals go on to build the planets. So we're sitting on things that used to be planetesimals. A few of them escape that fate, and they get processed into what now makes up the asteroid belt. So if we look at the asteroids, some of them actually look like what you would expect, which is a bunch of grains all accumulated together and compressed somehow into a rock, based on meteorites that are arriving at the Earth now. And some of them have got hot and separated out into a metallic iron core and a silicate mantle, the same structure as the Earth, so what we call differentiation. Well, when I started out in my career, there was a big debate about where that heat had come from, because we knew that the early solar system had been very radioactive, but radioactivity decays away over time. So although it generates heat, can you build planetesimals fast enough for them to incorporate this radioactive material and have it heat them up as they decay, so they go through this processing into cores and mantles of things. And that was solved quite a few years ago, where we found out that actually the planetesimals formed very early on, so they were formed early enough.
So when we're talking very early on, we're talking about the first few million years?
First million or so years of solar system history, fast enough for this radioactive decay to be around and so heat them up. So now we have a picture of how these things are evolving. So we have early formed things get hot enough to melt and produce cores and mantles. Planetesimals that form a bit later still get warmed up by radioactive decay, but they don't get hot enough. So then if you look at a planetesimal like that, you'd imagine it would have something like an onion shell structure, where things that got hotter were closer to the center and took longer to cool, and things nearer the surface wouldn't have got as hot because they were being cooled down by heat radiating away from the surface. So that's our model of what a planetesimal ought to look like, and it explains the range of material that's arriving at the Earth's surface today, because some of it's got hot and some of it hasn't, or it's got less hot, and so you think, well, this stuff is buried deeply on the planetesimal, this stuff was closer to the surface. So that's the backdrop to our understanding of meteorites and chronology and where everything fits into a big picture. So I worked on a system where we try and get dates from those processes based on the decay of a radioactive iodine isotope, iodine-129, which decays to a xenon isotope. You'll not be surprised to hear xenon-129. And that's called iodine-xenon dating. So that was actually the first such chronometer to be developed. It was developed, I think, iodine, that decay product was first observed around about 1960, actually.
Right. And that's a short-lived chronometer.
It's a short-lived chronometer. So the radioactive decay has a half-life of 16 million years. So it's all gone in the first 100 million years or so of solar system history.
So that means when you only find that particular decay product of xenon, it can only have come from that iodine isotope.
Yeah, so people looked at, when they first built mass spectrometers capable of analysing noble gases, they put bits of meteorite in and heated them up to see what they could find. And they found these xenon that just had one isotope, this decay product of iodine. And a bit later they showed that the minerals that have a lot of iodine had a lot of the decay product, and the minerals that have not much of it, which is you can then infer that the iodine decay has actually produced this stuff. And then based on how much of the decay product is trapped in a mineral, you can say what order it might have formed in relative to some other sample you look at. So if the iodine, if a lot of the decay product has been trapped, it probably formed early on. If not much has been trapped, then before it formed, a lot of it must have decayed, and so that's a late product. So you can see how a way of dating processes comes out of this radioactive decay. So on the one hand, people had this idea of that onion shell model, where things that had been processed a lot were cooling later, and things that had processed less were cooling more early on in solar system history. And then people started dating these samples using this chronometer, and they found it didn't correlate with what they expected. So there's a great paper which describes this as a puzzling early solar system chronometer that came out in the 1980s. And it's kind of interesting that rather than thinking there was something wrong with that idea of the heating and the cooling, they thought there must be something wrong with the chronometer. So the chronometer kind of fell into disrepute, if you like.
As much as chronometers can.
Yeah. So time passed, and I started working on this chronometer. One of the first things we started doing with our instrument, actually, was measuring things and trying to understand this. And I think it became apparent gradually through our work and the work of some colleagues in St. Louis, Washington University, that it's more complicated, because that model of just build an asteroid and watch it evolve under radioactive decay and cool down is too simple, and that actually these things were colliding and getting broken apart, and you have cooling rates. And I think that's kind of accepted now.
But at the time, was that something you knew, or were you just seeing whether the chronometer worked or not? Because the understanding at the time was that, okay, the chronometer doesn't work.
I think we set out really to try and test whether it worked.
Okay.
And the way you can do that is you can find other chronometers and see if you get a consistent picture. And it gradually, if you looked at it the right way, you began to see that actually we were getting a consistent picture among chronometers, and maybe it was this model that planetesimals were quite simple things where the problem lay. So that's the general background to this way of understanding the evolution of the solar system. But this particular data set we looked at, which kind of built up from some work, again done in Washington University, St. Louis, and another work on the same sample that was done by Greg Holland, who was at the time was one of my postdocs. And there's one of these samples which has not been heated up very much, so you can see the grains that it was originally constructed from very clearly. And if you take that, when that was taken apart, you try analysing them grain by grain to see what age you get, then you find out that things which are right next to one another in a rock, less than a millimetre apart, can have ages that are more than 50 million years apart.
Yeah.
So that's kind of puzzling, even in this idea that, maybe you heat something up and then an impact changes the fact that it can cool, and it cools a lot faster, and so everything would break that idea of the onion shell, but still you'd expect everything in the rock would record more or less the same age. And that's not what we observe. So, trying to think of another way of understanding that, and one option is that rather than getting energy to reset the chronometer from radioactive decay in a whole planetesimal, maybe it's because the surface, this thing is close to the surface, and there is a series of impacts onto the surface, and after each impact, something happens that can affect these different grains. Maybe they're happening in different places and then assembled together to make this rock, or maybe the way the impact shock wave propagates through the rock allows bits of it to record one age and be unaffected by another. And there are models now kind of suggesting that sort of thing can happen by people working at Imperial College model this sort of thing. So that gives us a sense that maybe it's impacts that we're dating with this thing, with this chronometer. So we started thinking about, well, maybe the distribution of ages through time tells us something about how the impact rate was changing in the early solar system. And that brings us, that was a sort of outline idea we had about 10 years ago now. And so it kind of led us into, well, what you expect to have been happening. And it turned out that astronomers look at this sort of thing and they've got the idea of a debris disk. We can move on from that stage of solar system formation where we talked earlier on about accretion, where you're building up planetesimals and then you've got millions of these 50 to 100 kilometre size things orbiting the sun, roughly where the Earth is now, you might think. And most of them go on to build the planets, and they've got others left over. What's the fate of the ones that are left over? And essentially, as other planets form, they start grinding against one another. So rather than growing now, they're being broken apart. Okay. And our asteroid belt today is remnants of original planetesimals that were broken apart and the leftovers of this breakdown process. And if you look out at recently formed stars, or when astronomers look out at recently formed stars, they find dust around a lot of them. And they call that a debris disk, something where you've got a population of leftover planetesimals and they're grinding against one another, and big things make smaller things, and they make even smaller things, and right on down until you get dust. And once dust is small enough, it can be lost from the solar system because it gets affected by the light from the sun, and it'll either spiral into the sun or the central star, or it will be blown out by the radiation pressure or the solar wind. So you've got this source at the one end of it, where you've got big things grinding together, and then they grind down till they make dust, which is lost. You've got a sort of steady state. And so you get a size distribution which just stays there, but the relative abundance of each is the same, but the overall abundance gradually goes away as the stuff is ground away. So you get a dissipating debris disk, which astronomers think lasts maybe about 100 million years, or it's that sort of time scale. So what we did in this paper was we tried to understand how the record of ages in these little grains of material could tell us something about the timescale with which that debris disk in our solar system was going away. And it gets to be quite a complicated model, because you have to think about how do these ages, how does things hitting the surface affect the ages you end up with. So for instance, it might be that something comes along and it creates a little mineral that records an age. What happens when the next thing comes along? Does it reset that mineral, or does it survive that? So there's are you wiping out the record continuously, or is something else happening? And it seemed that the model that best explains what we see is one where you start off with a loosely bound set of grains, and these impacts gradually compact it. And as they compact it, they process the material, creating little sites that can record an iodine xenon age. So a simple idea of what that might be, I'm not saying this is what happened, but as an illustration, if you create a load of grains and some of them are ice, as an impact comes through, it melts the ice grain. The ice then reacts, the water then reacts with adjacent minerals to produce a clay mineral, and that is what's recording an age. Well, if that's what's happening, the next impact that comes along isn't going to reset the age, because it's not got the ice there. It might create another age somewhere else where another ice grain melts, but you won't overwrite the original record. And what we saw seemed to be best explained by this model of creating sites that record ages, rather than starting off with a bunch of sites that have recorded an initial age and gradually overwriting them until you see the record which you see today. So once you've settled on that model, the next problem is that there's two things which can be determining the distribution we observe today. One is that the rate at which impacts are occurring is declining with the debris disk, but the other is that the sample's ability to record an age is disappearing, because each time you consume a little ice grain in that very simple model, you've removed one potential place that could have recorded an age. And so out of that model comes a constraint that it took quite a long time, a few tens of millions of years, was the timescale of debris disk dissipation. So to get what's the longest timescale it could have been, we had to look at some other work we'd done in the past, where there's another part of this primitive material, which is grains that arrived into our solar system and weren't processed. They just got incorporated into the planetesimals, things called pre-solar grains. And some of these record some of those stars that are synthesizing particular xenon isotopes. And we'd shown in the past that one set of these things, which are called nanodiamonds, actually they incorporated some of that radioactive iodine isotope. So now you've got, if you look across the solar system, you have a uniform thing where you've got these little nanodiamonds everywhere. They all come from the same place. They all have the same concentration of this radioactive iodine isotope. So they're an independent measure of how things were processed subsequently, and how much of the decay product they've retained is a measure of when processing stopped, if you like, or when things stopped losing xenon under this kind of impact flux, or whatever else is causing them to lose xenon. So we look at these nanodiamonds, and we don't measure each nanodiamond, because only 1 in a million has even got a xenon atom in it at all. So it's a bulk measurement. So when we look at how much of the decay product they've retained in a sample, it's an average of some of them that were processed early and some of them that were processed late. So we get this information from it, and it gave us a sort of upper limit on the age, on the time scale of the debris disk of around about 50 million years. So it looks like, putting those two things together, the time scale over which the debris disk dissipated was in the region of 40 to 50 million years, which is kind of what is consistent with the observations of debris disks around other stars. And it tells us something about how very small scale material was delivering things to the terrestrial planets through their first 100 million years or so of solar system formation. So that's the story of the paper we've published. Of course, we're basing it on one sample, and the test of this will be whether looking at other similar samples you get a similar sort of timescale out of it, or are we going to find that more complicated things were going on and that it's not quite as straightforward. So we've kind of put an idea out there which we and other people will test in the future, I'm sure.
I guess it's quite an interesting point then. So we're relying on what lands on Earth as meteorites to make these interpretations. To what extent do you think sample bias is affecting our view of what goes on in the early solar system?
Oh, I think there's lots of opportunities for sample bias in this and in a lot of areas of meteorite science, because the things we get are delivered from particular parts of the solar system. So we haven't actually uniformly sampled asteroids. And also, by definition, they're survivors. So we look at things that have survived the processes of the solar system, and even things that have survived the process of atmospheric entry. So, there might be less well consolidated, less well stuck together bits of asteroids that never make it into us for us to take. And that's kind of where sample return missions become important, because then you get a different sort of sample to look at. It won't be without its bias itself, of course, but you get a different picture, presumably, and that could well be an important test of our understanding of the solar system. And I think even over my career, as I think I've kind of explained, I've seen the picture of the solar system. The early years of the solar system has changed quite dramatically. So we're looking at over maybe 30 years or so.
And that's a function of recovering and understanding more meteorites, I guess.
Yeah, and developing technology which has allowed much finer scale analyses to be done, and new samples have become available in quite significant quantities. So
So is there a particular group of asteroids or a particular mission you'd like to see done to try and address some of these early solar system questions? Are there any easy targets?
I think it's not so much the asteroid as I think obtaining material which isn't overprinted by recent events. So whenever we look at the surfaces of planets, that's where we can get material from, but it's also exposed to impact fluxes and processing by solar radiation and so on. So could you get a really pristine sample from maybe a few tens of meters down inside an asteroid, then you might have stuff which has been less processed recently and so preserved a better picture of what was going on 4.5 billion years ago. It is a big ask, but I'm confident that you're up to it, guys.
Just bring the whole thing back.
Yeah. I don't think you know what the purpose of this podcast is. So just to brace the audience, Elliot has a phone-in question here for Professor Jamie Gilmour.
Okay, so something I've always
So please state your name and...
Hi, my name's Elliot, long-time listener, first-time caller. Something I've always been curious about early solar system chronometers is they imply some source, so a supernova or something near to the solar system. So is our solar system unique or fairly typical in that respect of having been near a supernova?
A very good question. So we look back in our history and we see these radioactive isotopes around in Earth's solar system. And as you say, they must have been made not long before the solar system formed. So by not long, we mean not more than a few half-lives before the solar system formed. So there's one which is particularly important, which is an isotope of aluminium-26. And that's what's responsible for heating up the original planetesimals. And it has a half-life of about 700,000 years. So it means that it must have been made no more than a few million years before our solar system formed, and because it's a massive star product, it means there must have been a supernova nearby. So the question whether this is normal, I've argued in the past that it may be that our solar system was shaped by this heating process, and that if this hadn't been present, there would have been a lot more water in the planetesimals that were accreting to form the Earth, and we would see, we'd be sitting here underwater. And a few people have kind of put this idea forward. So it seems the world would be different if it hadn't been here. On the other hand, we can't actually measure how much aluminium-26 is typically present. So you have to rely on astrophysicists to model how that happens and look at how stars are formed, how massive stars are formed, how you end up with massive stars near newly forming solar systems. And the models, there's a guy called Eric Gaidos modeled this about 10 years ago. Tim Lichtenberg's worked on it as well. And as far as I can see, it usually works out that around about 1 in 20 solar systems ends up with aluminium-26 in significant quantities. So we're in the 5% that have this happen.
So it's just a function of whatever star is supernovaing, basically.
Yes, and as stars form, they form in big groups. So essentially what happens is you have to form, maybe, let's say, a molecular cloud is forming stars over a few million years. Early on it forms massive stars. It also forms small stars, but those small stars don't get any aluminium-26. You have to wait for the massive stars to evolve and die and push this aluminium-26 back into the molecular cloud they formed from. So the later generations of these stars can incorporate some of the radioactive material, and that's kind of the way it works out. There's lots of things to take into account in the model, but they generally end up with few solar systems ending up with aluminium-26.
So before you have these massive stars exploding and releasing their aluminium-26, what causes the molecular clouds to collapse to form a star in the first place?
I mean, that's an excellent question. So, and I don't know the answer to it.
Yeah.
I mean, if you look at the spiral arms of the galaxy, I mean, I believe they're essentially little shock fronts where material, as it's orbiting the galaxy, is compressed slightly. And I think that's where you find the star-forming regions. But how the whole thing is bootstrapped, I think there's a general problem of, you can form stars once you've formed stars, but how a molecular cloud collapses before there have been any stars at all is an area of active research, I believe.
Classic chicken and the egg situation.
Yeah.
Okay, so something that we've asked everyone that we've spoken to so far.
To make you feel special.
Yeah. Well, it's just interesting to hear the range of answers. Is there something sort of outside your area of expertise and research, either in planetary science or outside in science and research, that you find particularly interesting or exciting?
I think one of the reasons I'm a planetary scientist, is that I find myself getting interested in almost any aspect of science. So I would say the answer in a sense is no, partly because, not because I'm not interested in other things, but because I seem to be interested in lots of other things. So I run a class in the 4th year on topics in planetary science where students can choose a research paper in the broad area of Earth and planetary science to study. And I pretty much find all of them absolutely fascinating. So the one we had yesterday was the impact of giant herbivores on the ecosystem in the Arctic. And there's so many things in that I'd never thought of, about how the plants that can survive and can sequester carbon, for instance, depends on the whole range of large herbivores that are there and how they interact with the plant systems and so on, and how people study this. It's just absolutely fascinating. So right now I would say that is something I'm pretty fascinated about, but it's been everything from dinosaur stampedes to magnetospheres of Jovian moons has been interesting in the past.
So you're like a science sponge.
Yeah, or a science gadfly to some extent. That I just the range of things people do, I think, is absolutely fantastic, and even across the school as well. We have such a huge range of science going on in this school that it's just fascinating. It's a real privilege to be able to dip into it all.
And I think it was just best to say it's been a real privilege having you on, Jamie. It's been absolutely incredible.
Indeed.
And thank you very much.
Indeed, thank you very much.
Thank you so much for having me.